We saw in Chapter 6, Part 1, that when electrons are placed around atoms, people can use quantum mechanics and do some kind of crazy math on it. We won't do the math, but we will look at the results of the math. And from the math, we saw that there were shells, subshells, and orbitals. And shells get the symbol N, sometimes called the principal quantum number. L, the subshell, sometimes called angular quantum number. And the M sub L is the magnetic quantum number. And they all have different reasons. In an atom, the punchline of the next several slides is that we're going to see that each orbital, which is where the electrons hang out, you can only have 2 electrons per orbital, okay? This is kind of the punchline of what we're going to start talking about. I use the analogy that, and I talked about it in Chapter 6, Part 1, how N is kind of like a street and the L subshell is kind of like a house, and in the subshell there are orbitals or rooms, if you will. And now we're going to talk about putting people in the room. And if you have to, you can put 2 people in a room. And that's similar here, but silly, of course, for how electrons go in orbitals. You can only have 2 electrons per orbital. The reason for this has to do with the 4th quantum number, which is called the spin quantum number, M sub S. And we didn't really talk about this in Chapter 6, Part 1. But in Chapter 6, Part 2, that's going to be really heavy. Now, M sub S didn't come out of the initial math on these things, believe it or not. M sub S wasn't seen. However, what happened is the guy in the right corner there, Paul Dirac, he combined relativity, which was Einstein's thing, with quantum mechanics. And when he did that, the M sub S term came out naturally. Woohoo! So score for Dirac. But anyway, M sub S was kind of the 4th quantum number to appear. It didn't initially pop in, but once it did, there's some really cool uses for it.
Any spinning electric charge creates a magnetic field. Spinning electrons produce magnetic fields with an identifiable magnetic polar orientation, so-called north or south. The polar orientation of a given electron is determined by the direction of its spin.
The real-world application, arguably, of M sub S has to do with how electrons spin. And in the video I just showed, the electron on the left was kind of spinning this way. All right, like if you were looking down from the north, it would look kind of like it was going clockwise. But the other electron was spinning in the opposite way. So again, if you were looking straight down now, it would look like it was going anti-clockwise. And electrons do this as well. And a spin 1/2, which is represented by the electron on the left, is a little bit lower energy than the spin on the right, which is the spin of negative 1/2. It's not a huge difference in energies between positive 1/2 and negative 1/2, but it is something that's important. And believe it or not, this can lead to the magnetism that's observed in atoms and ions. So along with M sub S, and along with the fact that there's only 2 electrons per orbital, we're going to talk a little bit here about magnetism because this is a result of the spin quantum number. In a diamagnetic system, you have electron spins that are canceled out. So remembering that electrons are spinning, and they either spin clockwise or counterclockwise, or as we're going to start talking about, up and down. If you have just as many up spinning electrons as down spinning electrons, we refer to this as diamagnetic. And a diamagnetic system doesn't have a magnetic moment, which means it's not a magnetic material. And most of the substances in our day-to-day life are diamagnetic. However, you can have an excess, if you will, of electrons which aren't canceled out, as in the diamagnetic system. So the lower left picture there, each of those arrows represents an electron that's spinning without something to cancel it out. And if you have a net imbalance, if you will, of electrons spinning one way or the other, up or down, works very well for this discussion, then you have what's called a paramagnetic system. And paramagnetic systems are actually small magnetic fields. All right, and they're a result of the electron spinning in one direction without something canceling the spin in the opposite direction. So in the diamagnetic systems, the ups and downs cancel each other. In paramagnetic system, you have a net number of ups or a net number of downs, whatever, that's spinning without anything to balance out. And that actually leads to some magnetic behavior. Ferromagnetic substances are like super paramagnets. And if you've ever played with little magnets and stuff, a paramagnetic material is something that approaches a ferromagnetic material, but it's not quite there. So if you have a true ferromagnetic material and you apply an external field, all of a sudden each one of the little individual paramagnets rises up and orients itself with the field. So in this picture, the black line represents an external magnetic field, and all those little randomly distributed paramagnetic systems all of a sudden now are all aligned to the top. And if they're all aligned in the same direction, all right, and if you take away the field, if that maintains itself, that's when they have then these super paramagnetic materials. And these are the kind of magnets you see picking up paper clips like on the right and stuff like that. Permanent magnets are just magnets, are magnetic systems that once you apply the field and you take the external field away, the magnet still maintains. And there's only a couple substances that will do this well. Iron, of course, is one, and nickel, and a couple other ones. But a lot of systems are paramagnetic, and we're going to talk about how to find out if an atom is paramagnetic or not, and then maybe make some suggestions as to when it could be ferromagnetic or even a permanent magnet.
Different materials have different magnetic properties. Liquid nitrogen is diamagnetic and is not attracted to the magnet. Liquid oxygen is paramagnetic. Paramagnetic substances in the liquid or solid state are generally attracted to magnetic fields. Liquid oxygen is held by the magnetic field.
This is kind of a cool video to me. Those two substances, which are both very cold, by the way, you'd have to have them much colder than room temperature. Anyway, the first one was liquid nitrogen, and liquid nitrogen is a diamagnetic system. It's not attracted to a magnet. So that black thing there was called a permanent magnet, really strong, but you put liquid nitrogen through and it flows on through, kind of like water would, if you will, like you'd think water would. But the second substance was liquid oxygen. And liquid oxygen, we're going to see in future lectures, is a paramagnetic substance. And paramagnetic substance will be attracted to magnetic fields. So while the nitrogen just flowed on through, if you will, the liquid oxygen actually stuck between the heads of the paramagnet, or the permanent magnet. So paramagnetic substances are very important. And there's a lot of uses for these. And in a day-to-day body, people talk about sometimes free radicals in the body and how free radicals can cause you to have colds and disease and aging and all this kind of stuff. Well, free radicals are just another term for paramagnetic substances. And if you have a paramagnetic substance running crazy in your body, you could have some issues. They can detect paramagnetic substances pretty easy. The diagram at the top there shows an electromagnet, like that black thing in the last video. And if you have a paramagnetic substance in that glass tube and you turn the magnet on, you can see how the pink substance goes more into the field as you go off and on. So the magnetic substance is actually attracted to the magnet. You can also then do things with angles down here. The lower right-hand corner shows some iron 3 oxide and stuff. So there's lots of ways to measure if something is paramagnetic that aren't too difficult. But again, if you had a diamagnetic substance and you turned that electromagnetic on, it would just sit there, no interaction. Same thing in the lower right. If you had a diamagnetic system and you applied a magnet, it would also just sit there. So it's a real interesting phenomenon when it comes to these substances. When all four quantum numbers are put together, here they are, n, l, and m sub l. And let's review real fast n, l, and m sub l. N is always a whole number starting at 1, and in theory it goes up to infinity in whole numbers. Never negative, never 0, etc., etc. Subshells have an n dependence. So as we saw in the last section, for example, when n equals 1, then l can only equal 0. L goes up to n minus 1. But if n equals 2, then L will be equal to 0 and 1. There are two possibilities. So you'll have multiple subshells in a given shell under the right circumstances. And this is similar to how you can have multiple houses on the same street, I guess. Anyway. M sub L, the orbital, depends on L. M sub L goes from negative L to positive L. And so M sub L depends on L, just like we saw L depends on N. So if you had an L of 1, M sub L would be negative 1, 0, and plus 1. If L was 2, M sub L would be negative 2, negative 1, 0, plus 1, plus 2, etc., etc. So those three are all kind of connected. Electron spin, the new player on the block, M sub S, has only two values, and those are positive 1/2 and negative 1/2. And those correspond to, if you will, orienting up with a magnet or orienting down with a magnet. There's no dependence on NL or M sub L. They're only positive or negative 1/2. So keep that in mind while we go through M sub S. Here's a question. It says, which of the following is not a valid set of quantum numbers? And this is something that we can talk about now because you can see how the patterns go. And it also helps to learn how the different quantum numbers work. Again, n has to be a whole number from 1 up to something big. All of those n's are okay. L can't be bigger than n minus 1. So if you look at D, for example, n of 3, L can't be bigger than 3 minus 1 or 2, and that's okay. In this problem, all of the L's are okay. They're no bigger than n minus 1. Now, M sub L depends on L. M sub L has to be between negative L and positive L. So if you look, for example, at B, L equals 5, M sub L could be anywhere from negative 5 to positive 5, and having a value of 0 is an acceptable answer, like we saw in Chapter 6, Part 1. So in this problem, all of the M sub L values are okay. However, as you can probably see, M sub S, as we talked about, can only be positive 1/2 or negative 1/2. Answer D here is not going to fly. No M sub S of zeros. You can have positive 1/2, negative 1/2, no zeros, no anything else.